Hi, and thank you for being patient and allowing me to present your lecture this week in video format. So I believe we were on slide number 61, right to the punchline. I wish I had half an hour more so I could have spent time in class going over Lagranges theorem, which I described as one of the most beautiful theorems in abstract algebra and one of my favorites. So here is Lagranges theorem in pieces. First, a lemma. If we have a function going from the left cosets to h, where h is a subgroup of G, and a belongs to G, it's a fixed element in G, and G is a group, and we define this function by phi of AH is equal to h. For homework, as your in-class assignment working together in groups, prove that this phi is one-to-one and onto. Thus, it's an injection. If you took a combinatorics class, this has meaning because if you have a one-to-one and onto function, it tells you something about the number of elements in the domain versus the number of elements in the range, namely that they're going to be the same. So Lagrange's theorem says that if G is a finite group and H is a subgroup of G, then the order of H must divide the order of G, as we saw with the examples from the dihedral group. So I'm going to present this proof step by step. I love this proof and I love this theorem, and I love to ask this one on exams, and I love to ask this one on comps. So the first step is the proof of the lemma that states that left cosets of H form a partition of H. I'm going to prove that lemma. Recall that I had stated it before earlier. So what do I need to show? First, I need to show that the union of the left cosets makes G. And second, I need to show that if I have two different cosets, left cosets, then their intersection is going to be disjoint. So this particular theorem is actually going to set up the stage, or this lemma is going to set up the stage for the proof of the Lagrange's theorem, and in fact it's the actual meat of the theorem. In your book, the way Fraley has structured the proof of this theorem is that he proves this particular step one elsewhere, and then in one shot he has the proof. So in your proof I will expect to see this part because the meat is all here, like I said. So here's the proof of the lemma. So let me take an arbitrary little g in the big group. To show that the union of all the cosets equal G, I must show that G appears in one of the cosets. So there is some coset with little g in it. Just in case Raymond isn't listening, I just want to check. Do you agree? Okay, Raymond, you agree. Let's move forward. So since the identity is an H by property of subgroups, then G star E is equal to G, and therefore by the definition of coset, it must belong to GH. And just to remind you, the coset GH is the set G star H where H belongs to H. And so I took a particular H, in this case I took H equals E, and then showed that by definition of the coset, the G star E is in the coset GH. So what can I conclude from this? I can conclude that the union of all cosets equals G. Let me back up a bit. What I've really shown here is that that the capital G group is a subset of the union of all the cosets, but it must be equal to the union because the union of all the cosets cannot be bigger than G itself. So therefore I have direction, subset containment in both directions, and that's really what I've shown. So continuing on, now I'm going to show that if I have two different cosets, left cosets, then those intersections must be disjoint. It's easier to show the contrapositive in this case. So the contrapositive of if P then Q is not Q implies not P. And in this case, not Q would be that if the intersection contains something, then AH has to be equal to BH. So if this is confusing, if the contrapositive idea, if you've not seen this or don't feel comfortable with this, contact me and I will put up another video, a short little video on logic and if-then statements versus contrapositives. But contrapositive statements are equivalent statements, so proving the contrapositive is just like proving the original statement. So I'm going to assume the if and between the if and the then is the no. I'm going to assume that this intersection is not empty. Then there's something in it. Then there exists a G that's contained in both. But if I know that G is in both of them, by definition I know that G is equal to A star H1 and G is equal to B star H2 for some H1 and H2 in H, because that's the definition of a belonging to a left coset. So because G is equal to one form and G is equal to another form, they're both equal to each other. And by the cancellation property of groups, I have that I can represent A as B star H2 star H1 inverse. Now because H is a subgroup and I take an arbitrary little h in the subgroup, H star H belongs to the subgroup also by closure. And so therefore we have AH belongs to little a, capital H, for any H belonging to H. In particularly, we have that AH, if I replace the A with my substitution from the previous slide, I have the second expression right over here. I replace the A, which if I use the associative property, I can rearrange the parentheses, and this guy here belongs to BH. What am I trying to show? I should have actually explained what I'm trying to show. I'm trying to show that if I begin with an element in this set, in this left coset AH, then that same element also belongs to the right coset. Therefore, AH is contained in BH by subset containment. Since I chose an arbitrary x belonging to AH, and that I showed that arbitrary x belongs in BH, I've shown subset containment. I've shown that little AH belongs to little BH. I could have done the same argument the other way around. It's a symmetric argument to start with little BH and show that it's contained in little AH. So therefore, I have set containment in both directions. Little AH is contained in BH, and BH is contained in AH. So therefore, the two sets must be equal. So therefore, I've done what I wanted to do. I've shown that the cosets of H form a partition of G. Step 2 of Lagrange's proof is to show that every coset of H has the same number of elements as H. Well, I'm not going to show this. You are. This follows from your homework problem that you must show that the function that I gave you, H into GH, is a one-to-one and onto function. I think I had GH goes to H, other way around in your write-up, but that's a one-to-one and onto function, and therefore the domain and range have the same number of elements. So in each one of the cosets, you're going to get the same number of elements as the original group, subgroup H. So this is a little lemma that you're responsible for. And the finale is, if I have n is equal to the order of G and m is equal to the order of H, then we know that every coset, we already know that every coset has m elements. But if there's r distinct cosets, we know by the fact that the cosets form a partition that I can rewrite G as a union of these distinct cosets by step 1. So I know that the order or the number of elements in G is equal to the number of elements of each one of these sets broken up, but that's equal to the number of elements summed up in each one of the sets because they're all disjoint. And there's R of them, so I know that the order of G is equal to m added up R times. Each one of the cosets has m elements in it, and there's R of these cosets, so I have to add the m R times and I will get the order of G. So what I have is that n is equal to r times m, and that's what we define to mean by divisibility. M divides n by definition of divisibility. That's a beautiful proof. And it's a proof that no picture can express, as in this quote by Francis Bacon. The best part of beauty is that which no picture can express. So a homework problem, this is probably a little bit more challenging. If I have a finite group with identity E, and H and K are subgroups of G, if the order of H is equal to the order of K, is it true that H intersect K has to be the identity? If you think it's true, prove your answer. If you think it's false, find a counterexample. If you feel like it's false, is there any condition you can add on the order of H and the order of K that ensures that this intersection will be E? So fix it and then prove your conjecture. I'm not going to go over the advanced slides, but they are definitely on my PowerPoints that I already loaded on Canvas. I am asking you to reprove all the big theorems of number theory using Lagranges Theorem. You can find these proofs anywhere on the internet. They're very popular, but it's the algebra version of the proofs. Alex took number theory from me last semester, and I did number theoretic versions of those proofs. But I love looking at the algebra proofs as well. I would recommend, if you're taking this track, to do the proofs, try to do the proofs yourself, and then check if the proofs are correct. Don't look at the proofs and regurgitate. That's a different kind of learning. All right, then, let me know if you have any questions. Work together. I'm around. I'm around by email and I'm around by cell phone, so you can definitely contact me if you need any help.